Okay, so we spent the first two lectures talking about matting, which is basically, how do you take an image apart into its kind of constituent parts, including the blending and the transparency that needs to happen for high-quality visual effects. And so this set of lectures is all about the kind of reverse problem of compositing. How do we take multiple disparate components, maybe from different acquisition times, and put them together into the same image so they all look like they live in the same world. So this is going to include not only this kind of conventional compositing, but I'm also going to talk in future lectures about things like removing items from the scene that we don't want. For example, removing a wire that's holding up a stuntman who's hanging in the air. So that will be the next lecture. So this lecture is on basically two things. So we're going to talk about what's called multi-resolution blending. And then we're going to talk about what's called Poisson image editing, or Poisson compositing. And so, in some sense, we already know a lot about how we should be able to take components and put them back together, right? So for example, if I want to make a new image, right, we already know that the matting equation should hold, right? I should be able to take the alpha channel plus the foreground plus 1 minus alpha channel times the background, and I get my new image, right? And so, in theory, the foreground and the background in a real visual effects shot usually come from different places, right? So it's like saying, okay, I have matted the alpha channel, I've matted the foreground off of some clean plate or off of some natural background. That gives me both my F and my alpha. Then I provide a new B, and then I use those to put together a new image, right? And so, in theory, that works great, right? But as we noticed, there's lots of effort that needs to go into making a really nice alpha map, right? And so that effort can be kind of burdensome. Wouldn't it be nice if instead of doing this, we could have somebody just say, okay, I'm just going to make a loose outline around this is what I want to take from image 1, and this is where I want to put it back into image 2. I'm just going to take basically like a drag and drop approach and say, okay, what if I just were to pick up this whole chunk of image, put it over here, and let the algorithm figure out the right way to stitch it together to make a nice looking composite, right? So that's really a neat idea, right? And so that's what we're going to talk about in the second half of the lecture. So, okay, and so all the stuff I'm going to talk about here is really related to, in addition to visual effects, all the kinds of stuff that you may be used to from, that basically every magazine ad of a model is touched up, right? So, the same kinds of ideas of touching up an image imperceptibly come into play here. All right, so back to multi-resolution blending. I realize I got off topic here a little bit. So this is the matting equation that we know and love. In a very hard-edged sense, if I chose my alpha mat to be equal to basically, 1 in the foreground and 0 in the background, right? Then that would be kind of like saying, well, my resulting image would look like the foreground where alpha equals 1 and the background where alpha equals 0, right? And so we already know that in general, images that are composited according to this way, right, where I'm just like cutting out with the scissors one element and putting it on the background, that's not going to work very well at all, right? You're going to see the line that goes around the the thing that I put in. And so in this terminology, I'm going to move from using F, B, and alpha to a slightly different terminology that's illustrated in this picture. So instead, I'm going to talk about basically the source image, the target image, and the mask. Okay? And so what that means is that the target image is kind of like the background part. I want to put stuff onto the target image, and I want to take some pixels from the source image and put them back onto the target image, and then this M right now is acting like a binary mask that tells me which pixels of the source should be put onto the target. And so, again, if I do this in a naive way, I'm going to see this obvious dark seam that goes around the boundary, right? And so if you watch, TV shows and movies from the 80s and 90s, oftentimes you will see this kind of ugly black line or weird mess that goes around the border of something. And so just as a kind of a side note, there's a great blog that you can take a look at called MattShot that talks about kind of all of these old school matting techniques, where basically you have actually mats, in some sense, a lot of these shots were accomplished by beautiful, detailed, huge glass paintings that were actually, originally they were put in front of the camera. And so the idea would be that you'd have this beautiful picture that the camera is filming through, and the live action kind of shows through the clear part of the glass. And so lining this shot up on the set was really challenging, but it produced some really beautiful things. And so, for example, here's the famous Indiana Jones, the end of the Raiders of the Lost Ark, right, where the guy's pushing the cart down this huge warehouse, right? And so this was the matte painting that went along with that, right? So basically, the gray part is the only part where the actual film shot shows through, and the rest of it was meticulously painted by an artist. And since the camera is locked off, meaning it's not moving, even though this shot has lighting and shadows and depth and so on, it all looks very realistic in the final composite. And here's a picture, again, I got this from the Matt blog website. This is kind of hard to see, but basically on the left-hand side you can see these guys are standing in front of a pane of glass that has a volcano painted on it. And so when that pane of glass, here you can kind of see on the left, here's when the glass is not quite aligned with the real shot, and here on the right is where the pane of glass is exactly aligned with the camera, right? And so this is the way that they used to do things old school, right? And the nice thing about it was that as a painter, you could put kind of a soft edge around the edge of the painting to let some of the foreground shine through, to do some of that alpha blending kind of in an old school analog way, right? By having paint that's not as opaque, right? So that's pretty cool stuff, and I encourage you to take a look at this MattShot blog for more details about how all this works, right? So, okay. All right, so what makes this matte line so visually obtrusive, right? One thing is that the human visual system is very sensitive to edges, right? And so if there's an edge in the image that doesn't continue smoothly across the transition, you will pick it up visually, right? So for example, if I have, this is my matte regions, this is my source, this is my target, right? You'll really see, for example, if there's an edge here that, doesn't continue the right way across the scene. And you'll also notice things like color changes, right? So if this side of the image is a slightly different color than this side of the image, your eye is going to that's going to introduce an edge in the composite that wasn't there before, right? So you're going to suddenly see a color edge over here. And so I believe next up on my PDF is an example of that. Oops, this here. So kind of here's an example of, if I have, this is my source, and this is my, this is my target, this is my source, and I want to put the cow in the foreground here onto the target. If I were to just kind of glue it in there with this mask, you would see that there's this kind of artificial line that goes around the cow in the shadow that was pasted in, right? Very visible. And so that's because my human eye is saying, hey, look, there's this dark edge between here and here that wasn't there before, right? So we need to kind of find ways to make the matte line, in some sense, as unobtrusive as possible for the human visual system. So one of the first ways that you could approach this problem is say, okay, well, suppose I don't have a great alpha matte for this environment. So today's idea is that we want to kind of do this drag and drop, cut and paste from the source into the target, right? And so the natural thing that you might think of is, okay, why don't I just kind of smooth across this line a little bit? That is, if I go back to this picture, that's like saying, well, everywhere inside the target, like fully inside the target, I'm taking target pixels. Everywhere that's fully inside the source, I'm taking source pixels. And in the middle, I'm just kind of blending in between. This is kind of like the equivalent of using an alpha channel. You can imagine that basically here, this dotted line is basically like the alpha matte for the source that goes from 0 outside the source to 1 inside the source. And here, this is kind of like a very crude, just like linear alpha matte, okay? And so then you could experiment with, okay, well, what if I was to change the width of this thing, right? So then it becomes an issue of, if I don't want to go through the effort of making a really good alpha matte, I want to use this kind of naive approach, well, I have to choose the width of this transition region. And so if I choose different widths, I get different results. And so here's an example where you can see that the edge of this is a little bit fuzzy. This is like saying I took the hard M image, the mask image, I fuzzed it up with a little bit of a Gaussian blur. Maybe this is like a 5-pixel Gaussian blur. And now if I put it back on the image again, you can see that this was not good enough, right? I can still see the boundary between the source and the target. So then I fuzz it up a little bit more, right? This is maybe like a 20-pixel blur. And if I look at that, I can still see there's like kind of this airbrushy effect that goes around the source and the target. And, unfortunately, the more I do that, the effect never really goes away very well. And part of the issue is that there is this kind of, color difference between the target and the source that's difficult to disguise over this fixed width band. And so one of the first approaches to blending images together that didn't use this kind of naive fixed width transition band was to say, okay, the human eye is sensitive to blending at different scales, right? So kind of what I'd like to be able to do is, the interior here, this source image, is a kind of a darker color than the exterior of the target. So what I might like to do is make the transition from the dark inside to the lighter outside to be really wide, right? So that's kind of like saying so for those of you that are signals and systems kind of people, from a signal processing point of view, it's like saying that I want the low frequency stuff to be blended over a wide transition region, whereas I want the high frequency stuff, the edges, to be blended over a short transition region. And so this was the insight of a famous paper by Burt and Adelson where they proposed this basic idea. So the idea here was multi-resolution blending. I should do blend low frequency changes across wide transition regions. And conversely, I should blend high frequency changes across narrow transition regions. And so, in some sense, what we need to do is kind of do, one way to think about it is kind of like a frequency decomposition of the image where I take, the low frequency parts of the image, the high frequency parts, and I treat those in different ways, okay? And in this case, these guys propose to use what is a very common image processing computer vision technique called the Gaussian pyramid or Laplacian pyramid. Has anyone ever heard of this? Okay, so here's the idea. So what I do to make a Gaussian pyramid is I basically assign a kind of a small blurring kernel. Okay, and this could be, for example, a 5 by 5 Gaussian, and so remember what a 2D Gaussian looks like. It kind of looks like a hill that is high in the middle and low on the ends. And so what I need to do is make a discrete version of that, and there are various ways to do this. If you just ask MATLAB for an n by n Gaussian blur approximation, it will give you something, and there's an example in the book. Basically, I'm not going to put all the numbers in, but like, for example, this number is 0.6, and these numbers are 0.25, and then these numbers are smaller, and the numbers around the front are smaller still, right? So basically, you can make this kind of digital approximation to a Gaussian shape. And so what happens when I take an image and I blur it, well, or when I apply this filter to it, well, it looks blurrier, right? And so the idea is that what I do is I build a series of images where I have, let's call this G0. This is my original image. And then I can blur this image. What I do here is I would say this is like G0 convolved, let's call this kernel K. Kernel K. Does anyone else watch Danger Mouse? All right. So G0 convolved with K is a blurry version. And both of these guys are at full resolution. And then a Gaussian pyramid is constructed by now reducing this to be half the size in both dimensions. And so this is like G0 convolved with K, and in the book I have this notation that says downsampled by 2. And so I call this G1. And the idea is I can keep on blurring the image and making it smaller and smaller, okay? And so a Gaussian pyramid basically looks like, you know, increasingly smaller and increasingly blurrier versions of the original image. Okay, question?
If you use a different, like a wider or a thinner kernel, does that change your shrink size per step?
No, you always downsample by 2. Right. So yes, you can change this Gaussian kernel if you want to be 3 by 3 or 7 by 7, but you always downsample by 2 at every step. Yeah. Okay. So how does this help us? So if I think about this image and this image, right? So this is a blurrier image of this. And so if I subtract the two, what I should say is, okay, well, in low frequency areas where the image color is not changing too much, then this and this image are basically the same, because blurring something that is already low frequency doesn't really change things that much. What will change here are basically the fine detail edges in the image, right? So the edges here will get a little bit blurrier than the edges over here. And so when I subtract these two, what remains is just the finest detail edges at the top image. And actually, maybe I should just do a MATLAB example just to show you, but I just want to do it in paper for a second. So basically, if I look at this guy minus this guy, what I get is an image that I'm going to call L0. So again, this is the original image. This is the blurry image. And then this is the edges at the highest resolution. So to make this a little more concrete, let's go to MATLAB, because MATLAB makes everything better. Okay, so yeah, creepy. We're going to come back to creepy later. Let's see. Okay, so this is an image we're going to come up to later, but let's say that I were to make this grayscale, so RGB to gray of T. Bring this guy here. Okay, so here's a grayscale version of my hand. And now what I could say is, okay, I need to make a Gaussian filter, and so I believe that I need to do that with F special Gaussian 5 by 5. Right? So here, if I basically, what's the easiest way to do this? If I were to of course, this is some like super tiny image. But if I were to make this a lot bigger, I need to make it really big. Why will you not embiggen? Okay. So let's suppose, just for the sake of argument, I make a Gaussian image that is 50 by 50. Okay. Oh, I see. I know what's wrong. Okay, so let me just do help F special to see where I've screwed up. So basically, F special lets me make all sorts of filters, disks, squares, etc. And so this is a Gaussian. And so if I look at what actually I have to do, I basically am giving it a size. That's basically the physical size of the filter. And then sigma tells me how wide the Gaussian is. And so if I were to say, okay, I want a 50 by 50 Gaussian, and I want the variance to be like 10. Now if I look at this, it should be a little bit more visible. Right, okay. So now I've got this blurry Gaussian kernel, and then what I could say is, okay, my blurry guy is going to be what I get if I filter my hand image. I guess I have to supply it with the Gaussian. Oh, actually, no, I want to do imfilter, I guess is what I want to do. So clearly I should have prepared this before class. Let's just see here. So, what don't we like about this? Imfilter. Let's just look at the reference page. I guess I have to supply the image first. Finally. Okay, so now if I look at imshow blur, this is a blurry version of my hand, right? And actually this is a little bit probably blurrier than I really would want. So let me just make the Gaussian blur, let me bring the G back to the G that I wanted to start with, which was a 5 by 5 Gaussian. Now if I blur that, no, I'm just using the default sigma in this case. So here, this figure, it's probably hard to tell, is a little bit blurrier than the original. In fact, it's probably pretty hard to tell that there's anything different about it. So maybe to make the point a little bit stronger, let me just make this a slightly bigger Gaussian with a slightly larger variance. Okay, so we can all agree this is a slightly blurrier version of my hand than I had before. Okay, now what I want to do is make sure that everything is the same size, right? So everything is still a 512 by 512 image. And then what I'm going to do is I'm going to make a L0, which is the difference between my original image and my blurry image. When I do that, let me just make this like this. So when I do that, what I get is an image that looks like just the edges of my hand, right? And so you can see that in regions like the wall, where it was all low frequency stuff, right? There was no real variation on the wall. That means that the difference between the original version and the blurred version is basically 0, which is represented by this gray. In places where there's a strong edge, like this edges of my fingers, the edges of this lamp, the edges of the desk, all that stuff kind of shows up as an edge in this Laplacian, in this difference image, right? And so you kind of see there's a little bit of a, if I was to zoom in, around every edge there's, you know, kind of like a little bit of a black where there's a big negative difference and a little bit of a white where there's a big positive difference, okay? And so that's the basic idea behind this picture that I was just showing you here, which is just what I showed you. Original image minus blurry image gives me some edges, right? And now if I keep on doing that, right, so if I was to keep on making the difference between the image and its blurry version at every level, what I would have on this side would be basically increasingly smaller and blurrier versions of the original image. And over here I'd have increasingly smaller versions of the edges that are important at every scale, okay? And so the result of this is that I get what's called, on the top, I get kind of what's called a Gaussian pyramid. Right, so this is like my Gaussian pyramid. And on the bottom, I get what's called a Laplacian pyramid. And then I'm going to make a, basically, at the very lowest level, this is basically like the tiniest, blurriest image. And then these things are basically the edges at different scales. And so the idea is that since I created every one of these images by basically subtracting corresponding original and blurred images, if I wanted to, I could get back the original image by saying, okay, I'm going to take basically, you know, the bigger, you know, so basically I could say I'm going to add up the edges at all the different scales. As long as I add them up to get the resolution of the original image, I'll basically be able to reconstruct the original image. So let me just show you with an example on MATLAB here. So here's an example of a Gaussian and Laplacian pyramid for a real image. And so here, sorry I can't fit this all on the screen, so on the left-hand side I have the full resolution image, and then as I make the Gaussian pyramid, I get basically smaller and blurrier versions, right? So if I was to blow G4 up and look at it at full resolution, it would look like a really, really blurry image compared to G0. Okay. Yeah?
Just really quick, in your downsampling, are you essentially just taking every other pixel, or how are you getting the downsampled image from the margin?
So in each case, I'm not just taking every other pixel, I'm actually blurring it with the Gaussian before I downsample.
Right, so you're blurring the Gaussian, then you're just downsampling every other pixel at that point, or how do
Oh, I see what you're saying. Yes. So for the purposes of downsampling, you can imagine that I'm taking every other pixel,
Okay.
right? That would be.
So I'm just trying
yeah.
to, because I mean, depending
Yeah,
on
yeah.
how you downsample, it might.
Right. Yes. So yes, that's okay. You can imagine this is just taking every other pixel. That's fine.
Okay.
Yeah.
But wait, my question is not imagination.
Right.
Like, when you downsample, are you actually doing that after you apply the downsample?
Yes.
Okay.
Right. So yes. Roughly. Yeah. And then here are basically the Laplacian images, right? The edge images. And so here you can kind of see that the L0 correspond to kind of the finest edges in the image. And then as I go up the pyramid, or go down the pyramid, I guess, I get edges that are kind of significant at smaller and smaller scales. And so if you think about it, you know, the edges here in, for example, L3, these are things that are like the most critical edges in the image because they're still visible when I have the really blurred tiny images and I compare them to each other. Yeah, question?
So why wouldn't we just look at, say, the discrete horizontal and vertical derivatives of the image? Because that will also give you edges.
Yes. And so you're right, that basically if I were to use like an edge detector, right, I would get images that look very similar to this, right? And that's true. And so you can think about this as a special kind of edge detector applied to the image at every scale, okay? And so if you take image processing, right, you'll learn lots of different ways of applying edge detection to images, and one of them is basically like this Laplacian edge detector. And this is basically kind of like that, where I'm applying this particular edge detector at every scale. Okay. Okay. Other questions or comments? So the idea, oh, question, yes.
Wait, so the smallest Laplacian L, is it the same as G?
Right, so by definition, we have to stop taking the Laplacian pyramid at some point. And so at the point that we stop, at the scale that we stop, then I say that the lowest level Laplacian is basically the same as the super blurred G4, right? So yes. And so what I would do to reconstruct the original image is I would basically say, okay, I'm going to bring L4 up to full resolution, add the edges from L3, then I'm going to make that up to full resolution, add the edges from L2, then I'm going to make that up to full resolution. So basically I'm kind of like doing this accordion-like recreation of the original image, right? So to get back to the original, so basically to get back to the original, basically what I'm doing is I am taking the, I'm taking the sum of all of these Laplacian images, and here I'm kind of making a little upsample arrow to say what I do is I add up all of these images brought up to the right scale. And so that's like saying the original image is the sum of the Laplacian pyramid images brought up to, full scale. And the insight here is that if I want to, I can make my composite image by basically creating pyramids for my source image and my target image. So this is where it gets a little bit hairy. So basically for, you know, multi-resolution blending, what I would do is I would say, okay, I'm going to take Laplacian pyramids for the source. So this is going to be like Laplacian pyramids for S. And then I have a Laplacian pyramid for the target. And then I'm going to have a Gaussian pyramid for the mask, right? The mask is basically saying, okay, so which pixels of the source do I want from the target? And then what I'm going to do is I'm going to combine these things at every scale. So let's say this is like the Laplacian pyramid of 0 for the source. This is the Laplacian pyramid at 0 for the target. This is the Gaussian pyramid at 0 for the mask. And then I have like this. And so what I do is at every level, I combine these guys as if this is my alpha map. And so I kind of like say, okay, so my image composite at level 0 is basically, you know, take these pixels from the target times the Laplacian image of the target plus 1 minus this times the Laplacian of the source, right? Oh, actually, I'm sorry, it should be flipped around, right? I want to take the mask pixels from the source and then the other pixels from the target. And so what I do is I basically make a series of, basically what I'm doing is I'm building up the Laplacian pyramid of the composite image. And then to make the entire composite, I basically am going to add up these things from top to bottom. And so let me just show you a picture, I think that will make this a little bit easier to see. Oops, I had it here. So if I go back to this. So here's kind of what I mean. I want to zoom in on this. So basically, the top part is showing me, again, this is my source and target. So the left image is the target and the right image is the source. And so what I do is, this kind of is showing 3 levels of the process. So here, these guys are like the smallest, you know, the tiniest images, right? So this is like, actually, if we want to start at the top level, it would be more like this. This is kind of hard to see because the edges are so small. This is like saying, at the very top level, the biggest images, this is like saying I take the edges that are, you know, significant at very fine scales in the source and the target, and I combine those together with a map that is almost binary, right? So basically, this guy here has a very narrow transition region. And so when I combine them together, you know, it's almost like taking the cookie cutter out of the source and putting it onto the target, right? But at lower levels, right, so here, I've kind of shown these all at the same scale because it's easier to visualize. So here it's kind of saying, okay, here are some edges of the source and the target that are at a slightly, you know, lower level of the pyramid. And in that case, I want to blur those edges together with a mask that is visibly a little bit, got a wider transition region. And up here, at the very lowest level, when I have, you know, this is like the blurriest version of the source and the blurriest version of the target, and this is the blurriest version of the mask. When I combine those things together, I get the kind of blurriest version of the composite. And so basically, to get the final image, I add up all the images in the right-hand column, and I end up with an image that looks like this. And so here, this looks a lot better than it did before. Now you could still kind of argue, well, isn't there? You can kind of see there's something a little bit different, and part of that difference I think comes from just the fact that the source image has a little bit of a different texture than so the grass here has a slightly different texture than the grass over here, and so you can kind of see that maybe something has been done, but if you were to zoom in, you couldn't really put your finger on exactly where the edge of this image is, right? And so this is definitely a lot more successful than combining the images where there's like this one-size-fits-all transition band approach, okay? And so, this is a very old concept. I mean, this paper was probably written, I think it's written like in the mid-'80s, and so, this has probably been used in old, image processing papers, but it still works in a pretty decent way. I mean, it's still like the concept is good of thinking about, okay, I don't want to just smack these images together and uniformly blur the edge. I want to have what's happening is I'm actually combining different features of the image together at different scales, okay? And this idea of doing things at multiple scales, we're going to come back to that when we talk about things like multi-scale feature detection in Chapter 4.
No. Sorry.
Yeah, question.
Is it okay?
Yeah.
So going back to this original process over here on the left, in terms of your columns, it's the same plan in the book.
Yeah.
You're getting your right hand, the furthest right handmost image of the composite.
Yes.
Are you getting that by just adding the images to the left?
So I'm getting the rightmost image here by basically treating these two images as foreground and background and this as a map, right?
Okay.
So it's kind of saying this is the foreground, this is the map, this is the background, and I use the normal matting equation to produce every one of these right-hand images.
Okay.
Right.
So you're doing that with each one in the pyramid that you have on.
Exactly. So I'm doing each one in the pyramid, then I'm adding them up.
Now, the other question I had is why, because you have your source, target, Laplacian pyramids, why is the map pyramid then just a Gaussian pyramid as opposed to?
Well, because the map, so that's a good question. Why is the map pyramid a Gaussian pyramid? Well, so the idea is that conveys the concept that I want to take this original thing that is a binary hard-edged image, and I want to turn it into a wider and wider transition region as I go down the pyramid. And so I don't want to look at the edges of the mat, right? I want to look at the mat itself getting blurrier and blurrier, right? So that's the idea. So what you're seeing here is that here, this is like visualizing the mat at the highest resolution, which would correspond to a very, very wide kernel. I'm always using the same width of a blur. So really, when I'm doing this, these top images are all much, much smaller than these bottom images, right? So actually, I'm always blurring things with the same sized Gaussian kernel, but the images are smaller, and so the effective size of the blur gets bigger.
Exactly.
That's the idea. Right. So I mean, in theory, you could do all this at full resolution, but it would be a lot less efficient to do it that way, right? So the idea is that you get some efficiency gains by always applying the same Gaussian kernel at every level, as opposed to having to generate physically bigger and bigger Gaussian kernels and applying them to full resolution. So this is an efficient idea. That's also important. Yeah. Okay. Other comments or questions? Okay. All right. So I see a lot of dazed faces in the room here. So let's move on to something that I think is a little bit more fun and a little bit more intuitive, hopefully. Okay. So let's look here at a different example. So the images I showed earlier were we're in grayscale just because it's easier to, so you can do all this stuff in color, and I didn't do it in the book because I was limited by how many color figures I got to put in the book. So basically, you can apply this basically independently to every RGB channel and make them work together. So here's an example of a beach and some jets, and let's say, okay, I want to put these jets over here in this part of the beach. Now, if I were just to use the exact same method I told you before, the result I would get would be this. And so here, actually, it looks a lot worse on my computer screen than on the monitor. So this will come through when you look at it on the video. But basically, you can see that this actually doesn't look very good at all because the blue inside of here is on my screen, the blue is much more saturated than the blue of the sky here. And so even though I've done a great job blending across the edges, the fact is that the colors inside the source are just a little bit too different from the colors inside the composite. And so no amount of smoothing away the boundary is going to make that color mismatch go away. And if you look in the book also, I think that the book makes it really visible. There's this kind of smeary boundary where it's clear that someone has just kind of stuck this on and kind of smoothed across the edges to make it kind of fit in a little bit. Okay, so no amount of multi-resolution blending is ever going to get you past that issue. So what can we do to make that better? So the idea here is the following. So basically, multi-resolution blending fails if the colors inside the source and the target are too different. And so what can we do? Well, this is a really slick idea. I've always liked this algorithm a lot. And the idea is that I say, okay, I've got my source, I've got my target, and I've got my mask. And so for the purposes of this, let's suppose that I superimpose, so here's my mask image, here's my corresponding piece of the source, and here's my corresponding piece of the target. And so we're basically going to solve a problem that says, okay, you know, what's really important to make that source chunk look like it is in the target? Well, I mean, all the kind of important edges and texture and detail from the source have to make it into the new composite image. But it's not like super critical that the exact colors are maintained, right? Because you're not necessarily going to know what the original source maybe looked like. So, you know, as long as the relationships between pixels, like the difference between a pixel and its neighbor, as long as all that stuff is really preserved, then I expect that the composite will look good. And so the idea is, you know, the edges inside M in composite must look like those of S. And the colors on the boundary, so this little weird notation means the boundary must match those of T. So basically that's like saying that, you know, inside the mask I need the edges to look right, and then right on the boundary, on this boundary of the mask, when I take this chunk and I put it into here, there can't be any mismatch at all. The colors have to match up precisely right around where I put that image in, right? And then the idea is that what I'm going to do is that sets up basically kind of like an optimization problem where it's saying, okay, I want the I want the boundary to match exactly, and I want the difference between the edges in S and the edges in the composite to look as good as possible, okay? And so let me try and write that a little bit more mathematically. This is like saying I want to minimize, and here I'm going to put things in, kind of continuous terms. Even though we have a discrete image, I'm going to talk about the discrete version of this in just a second, so don't freak out. So basically this is like saying I want to have the difference between the gradient of the image and the gradient of the source. I want to make this as small as possible, and I want to make this, basically inside the boundary. And so here I'm going to kind of change gears and just say that I'm going to rename the mask region to have this omega, only because this kind of matches up with the way people talk about boundary problems. And so here, this is basically omega is the inside of the mask, and this d omega is the boundary of the mask. So this is like saying everywhere inside the mask, I want to make sure that I minimize the difference between the image I create and the source. And so here, I have the ability to choose these, I have the ability to choose these XY position, or the images, right? I guess maybe I should be careful. So, I like this the first time. So what am I optimizing? I'm optimizing the image colors of the composite inside the boundary. And then I have a constraint that says such that on the boundary, right, the composite colors I choose have to exactly equal those of the target. Okay? And so this conveys our intuition, hopefully, that, you know, stuff needs to match up exactly on the boundary, otherwise I'll see a visible seam. And then inside the region, I do as well as I can, making the edges look as good as possible, right? Okay. And so I will save you the mental anguish of getting from here to the way that you actually solve the problem. But so basically, just for those of you that are interested, so this is a variational calculus problem. And there are ways of going from a minimization problem that looks like this to a solution, okay? And so here is the solution. And so I'm going to define my terms here in just a second. Right, so for those of you that, so everyone hopefully one day back in the day you took vector calculus, right? So this del square is basically like the second derivative, okay? So this is like the kind of two-dimensional second derivative saying that basically I need the 2D derivatives of the image and the source to match up inside the region, and this is the same constraint that kind of carries over from over here. And so let's talk about exactly how this works in the discrete world, right? So the discrete world is one in which we only have pixels, right? We don't have any nasty, you know, continuous integrals or anything like that. So basically, the discrete version is actually much easier. So let me just say, what is the del squared operator? Is simply a digital filter. And what I mean there is that that's just like taking this, here's an example implementation. This is like saying I take this very simple 3x3 filter and I run it across the image, okay? And so this guy is, you know, built into, so actually if you look at, I'm just going to say there's this nice MATLAB command del squa that will be helpful in dealing with this stuff. And so how do I take my, you know, equation here and turn it into a thing that I can use in MATLAB or somewhere else? Well, here's the thing I need to implement. Well, this is just basically saying, well, I take the -4 times each pixel I'm at, plus, you know, the pixel above me, the pixel, actually if I'm doing this, actually it's like the pixel to the right of me, the pixel to the left of me, the pixel above me, and the pixel below me. And these things have to be equal. Right? All this is saying is that there are knowns and there are unknowns, right? So the knowns are all the S and T values, and the unknowns are the I's that I want to create, right? So this is like saying, well, you know, I want this here to be equal to this here, okay? So all this stuff is unknown, and all this stuff is known, okay? So let me just show you a picture here for a second. So there are basically different kinds of pixels we have to consider, right? So if I consider that basically, you know, the light gray region is the stuff I need to fill in, and the dark gray is basically the boundary, like the digital boundary of that region. So here, for example, pixel A is fully inside the region I need to color in. And so here, I would apply exactly the equation I just wrote. What'd I do? Come back. I would apply exactly this equation at a pixel like pixel A, right? Because that's fully inside the source region. And so pixel B is like just on the edge of the region I need to fill in. And so it is that now pixel B is going to say, okay, this is where the constraint comes in. This is where the constraint that says I need to match on the boundary. And so here, pixel B is going to use some unknown values, and then some known values here. And this is like saying the values of these gray pixels need to be exactly equal to the target. And so this here applies to pixels kind of fully inside the mask. For stuff that's not fully inside the mask, for example, let's suppose that I have this situation where I have like this is my boundary, and these are pixels I need to fill in. So let's say I'm looking at this guy here. This would be like saying, okay, so I still use my formula for this Laplacian, and so if I call this like x, y, and this is x minus 1, x plus 1, y minus 1, y plus 1. And so here, this would be like saying, okay, well, this I don't know, this I don't know, this I don't know, this I do know. This has to be exactly known to be the target color here. And this I also know. Right? So this is like enforcing the boundary condition to take place. And then, you know, the source part carries on like it did before. So this is for pixels, you know, adjacent to the boundary. Okay? And so every pixel is basically in one of these two cases. Either I'm fully inside the region or I'm adjacent to the boundary, right? So that means that for every pixel in the region I want to fill in, I'm either using this equation or I'm using this equation, right? And so this turns into basically a big linear system that looks like a big matrix times, you know, all the intensities I need to figure out. And then this is, again, this thing is full of, you know, I guess the way I think about this is that, you know, these guys are full of numbers, probably, you know, 4s and 1s. The 4s and 1s coming from these 4s and 1s. And these numbers here are coming from S's and T's. Okay? And so it's pretty easy to figure out what should this linear system look like. So basically now I've got one equation in 5 unknowns for basically every one of these lines generates one equation, right? And so if you think about it, actually, since every one of these things depends on at most 4 or I guess at most 5 of the elements of I, that means that this is really a big sparse matrix, right? Lots of zeros, okay? And so this is a very, you know, easy system to solve. And so if I was doing this in MATLAB, if I call this A, I call this X, and I call this B, then my X would just be like A \B, right? That's the way I would solve things in MATLAB. And so this is one of your homework tasks for next homework is to code this up, right? And actually, it's not that hard. I did it myself. I'll show you my implementation so you know it can be done, right? But then once you've got this, it's a lot of fun to be able to use it, okay? And so here's an example of, you know, so here is the JETS example that I did before, but this is with the now Poisson composite, okay? And so here, again, maybe you can't tell the difference so much on the screen, but it's much more visible in the book. There's this kind of nice gradient, for example, in the original target image of the blue of the sky, and that looks exactly like these planes just belong there, right? So I mean, again, if you had seen this original image, you probably would not have thought that anything was wrong. Here's another image that I didn't put in the book. because I thought it was too creepy. So I thought this was fun to do, though. We'll do this one live. So here is the target image, and here is the source image. And so what I did was I cropped out my hand, and I cropped out my eye, right? So I want to put my eye inside my hand, okay? So let's do this in MATLAB. So where's my MATLAB? Okay. So my source is going to be my eye, right? You. I choose you. And my target is going to be my hand. And my mask is going to be this thing. So if I show, let's make sure that everything is copacetic here. Oh, that was dumb. I meant to clear all my figures. Close all, that's what I want to do. Okay, so make sure everything is still good. So this is my source, right? I just cropped out the eye. This is my target. And so here I need to be careful to make sure that when I did this cropping, you know, I had to make sure that I aligned the target and the source exactly the way I wanted to, right? So I mean, you have to make sure before you do this that the pixels of the source and the target are physically in the same places. Otherwise, your target is going to appear, or your source is going to appear in a different place. And then my mask, so here what I did was just cropped out the eye. So it's 1 where the eye is and 0 where it's not. And so I'm just making this a logical image, which means it's absolutely 0 or 1, because apparently that's the way that 3 years ago me decided to code this up. And so let's look at my MATLAB just to show you that it works. So you know, here basically, I guess I shouldn't show you this too much because you have to do it in the homework. So I'm going to scroll through real fast. Oh man, I've already made the homework hard. All right, so basically all I'm doing is I'm building up the A matrix, basically this big sparse matrix, and I'm forming up what is the right-hand side. And so now the magic is that if I make my composite is my Poisson, where I ask for the source, the target, and the mask, then I get this high-quality, creepy image, right? Where again, you know, it looks pretty good. I mean, even if you zoom in, it looks all right. So you too can make this creepy image on your own. And so part of the homework is to basically do this with source and target images if you're choosing, and see how well it works. Okay. This I deemed was a little bit too sketchy to put actually in the book. So, all right. So let me just make a note about when. So this is the result. So this is an example of where it doesn't work. Okay. So just a comment that, you know, here this was the region that I put the planes in before. What if instead I wanted to put the planes over here, right? So if I do that with my standard technique that I just told you about, I end up with something that looks kind of like this. And this is bad, right? Because it looks like the target intensities are kind of smudging up into the plane, right? And so this is bad because I've kind of chosen a bad region for my kind of mask contour. It overlaps this important edge in the image, okay? And so one way that you can get around that is by doing what's called a mixed gradient approach. And so let me go back to my thing here. So just a note that kind of the idea here is that, again, this requires you to kind of remember back to vector calculus a little bit. So originally we said that we were saying that the del squared of this had to equal the del squared of that. And actually, you know, I guess I maybe have said it verbally, but this is also often called the Laplacian. And so actually, if you think back to the Laplacians that we did in the matting section, this is the same Laplacian, basically. So this is basically like a two-dimensional, like the two-dimensional second derivative. Question?
Yeah, so basically the lesson is that the original method really only good for if you have like a smooth gradient?
So yes, I mean the original method is really good when you're not plopping your target, you're not plopping your source down to somewhere in the target that is like really busy, right? So I guess you could say that that's good for places where the target has a low gradient. That's not a bad interpretation of it. Okay, and so here, this is maybe a little bit subtle, but basically, in this case, the right-hand side is saying, okay, I've got a source that I need to use, and I'm going to take the Laplacian of that, right? But there's actually no reason that I have to use the Laplacian of a real image. And one thing I could do instead would be to say, for example, okay, I am going to use, so how do I want to say this? So here, the difference between these two things is that this is like saying this is the Laplacian of some real image. And this is like saying this is like the divergence of some arbitrary vector field need not come from real image. Right? What I mean by that is that, if I take an image that I'm starting with and I take the, gradient x and y, right? There are some constraints among those values. I can't just have like an arbitrary x gradient and an arbitrary y gradient and be able to say these correspond to original image. However, there's nothing in my formulation that says I can't just take some arbitrary vector field and then basically look at the x and y derivatives of it. So basically, this produces the same kind of result as this, but here, this could come from anywhere, right? And so, for example, I could say this is kind of like, so let's say mixed gradients. So I could use something like this. Let me just write this down first. So this is kind of slangy. This is like saying, okay, well, if I wanted to, I could make a vector field that said, okay, I should use this thing being the gradient of the original source if the source edges are stronger than the target edges. But if the target edges are stronger, I should use those, right? So it's kind of like saying that now, if I think about this whole thing taken together, this is not the gradient of some actual original real image. This is like a mixture of gradients from two different images, right? And so the idea here is that here I'm only using whatever edges are stronger at the source of the target at a given pixel. And so in the plane example, that's like saying, okay, I know that in this region here, the edges of the target, this mountain, are much stronger than the edges of the source. And so here, I want to preserve these edges, right? Whereas over here, where the target is relatively blank and the source with the planes is really edgy, here I want to use the source edges. And so if I put those things together, this is like the before shot and this is the after shot, right? So now you can see that all the edges from the target that were there before, like the mountain and also these clouds, right? So these clouds here were in the target, but they weren't in the source, but they now appear in the composite, right? Whereas up on the upper part of the boundary, all these edges obviously are much stronger than whatever was originally in the target. So now this is kind of like something where I'm combining the two things together, okay? This is what I call a mixed gradient approach. And so you can implement this on the homework if you want to. It's not that hard to do once you kind of get the hang of it. And that allows you to make some even more realistic looking composites. Now, all that being said, there definitely are some cases where even this is not going to look very good just because the color mismatch is too much. Like if you take, like a bright red object and you put it in the middle of a bright green target, nothing that you do is going to make that look like it lives in the world, right? So probably what will happen is that you'll get, everything will look like a green kind of weird tinge. So actually, if you look at the original Poisson, so this is, I guess I didn't really even say what this is called. So this whole process is called Poisson image editing. And it was an original paper by Perez. And the reason it's called Poisson image editing is that when you have, when you have equations that look like this, these are called Poisson equations, right? So the system that I'm trying to solve that came out of solving this variational calculus problem, that's called the Poisson equation. Actually, those of you that have taken some, I'm sure that you must have seen like the heat equation in physics at some point, right? So the heat equation is like saying, okay, I clamp the ends of a bar or I clamp the periphery of a plate and I tell you what is the heat that's on the boundary, and I ask you to tell me how does that heat diffuse into the center, right? So you probably had to solve those kinds of heat equations way back in the memory of taking like physics 2, maybe, I don't know. And so these are the very same equations applied to image compositing, right? So in some sense, this is kind of similar to, it's kind of similar to the heat equation. It's like saying we clamp the boundary, we know what's going on there, and then I want to let that diffuse into the middle of the image, subject to the constraints that I want these gradients to look as good as possible, right? And so that's kind of like the difference between a Poisson equation and a Laplace equation is whether your right-hand side is 0 or not. Okay. And so as you can see, this is a neat technique. And so one of the things on the next homework is to implement this yourself, try it out, see how well it works. And let's see what else I wanted to say here. Okay. So one nice innovation that kind of operates on top of this was a variation that they called drag and drop pasting. And so the observation is that, to make this kind of thing, I still had to manually outline the jets. And I had to say, okay, I want them to go here, right? But in practice, a human is not necessarily going to be so picky about, I really need the boundary to be like right here. I mean, typically what happens is that you can tolerate some slop. And so the picture here that I want to get to, if I get my menu straight. So the picture here is like the following. This is like saying, okay, maybe, maybe this outer outline here is the one that I drew, okay? But as a human, I may have drawn that outline to be more conservative, okay? Instead, what I could do is I could write an algorithm that would find me the best contour that was kind of just inside my outline that would have the lowest error in building this composite, right? So you can imagine that, what would that mean? For example, maybe I could say the lowest mismatch. Well, so what we naturally can do would be say, okay, I want to find a contour that already matches the target pixels as well as possible, right? That would make my Poisson equation have to work less hard to make the composite look good, right? So what I want to do is I could say, okay, for example, I could add up all the differences between the source and the target around this boundary, and I could find the lowest cost boundary, and I could use that for my Poisson equation instead of the thing that my user originally drew. And so that was the idea of this drag and drop pasting, was that the user drew the light line. The inner line here was basically like a hard segmentation that came from grab cut. So it's like saying, okay, suppose I outline those planes. Well, the outer boundary is what I drew. The inner boundary is something that really tightly conforms to the outline of the planes. And in theory, any boundary in between those two curves should look okay for the composite, right? And so find me the best boundary that it lies between the grab cut boundary and the user segmented boundary. And again, you can actually find this best boundary using dynamic programming, so it's actually not such a hard thing to do. And then your composites look better than the ones that you would do if you just kind of were forced to use exactly the original boundary pixels. Another kind of thing that was kind of cool was you could extend that idea even more to say, okay, maybe you just say, okay, I need to put a car here, right? And I've got a library of a whole bunch of cars. So you could kind of extend this to say, okay, instead of looking at a specific source region, I just have a whole bunch of source, I've got a source library of cars and trucks and so on, and I say, okay, put a car here in this image and put a car over there, right? And then my algorithm goes off and says, okay, what would be the best car that fits into this region to have the lowest mismatch between the source and the target, right? So in some sense, I'm choosing from a library of possibilities. And so actually, there's this kind of cool, like, kind of clip art-based method of compositing from a given kind of named set of cars, trucks, and so on. And so that's a kind of a neat extension. And I think, let's see if there's anything else I want to say. Just in general, I guess I would say that for a while, this kind of notion of operating in the gradient domain, where I was trying to get edges to match up instead of getting colors to match up, was a very popular idea. And a lot of good algorithms for things like high dynamic range compression and changing illumination and so on, a lot of those things are done in the gradient domain the same way that we talked about here. So that's kind of a neat general technique to use. Okay, so let me stop and ask if there are any questions about anything. All right, so let me just pause my